Hello, welcome to another stream of Caveman Coding. Today, I logged in late actually. It's 11:44, but still counts because it is um you know it's not the next day, so it's still before 12, so still counts. I'm tired because I went to college and stuff, but I've got a clock in. So let's try to do at least a little bit of programming. So yeah, without wasting time, today we will be doing the same thing that we were doing the last stream. We were on boot. We were making a NOS in 1,000 lines, so that's what we're doing right now too. So the last time, what we did was actually show you. So, well, if you think about it, so this we did kernel.c and we produce kernel.elf using the shell scripting run.sh. If I show you run.sh, what it basically was is set xue, which is um oh forgot I forgot actually what is this xue, and then we use qemu. Xue is basically just setting up the shell options basically, and then we use QEMU using the RSV 32-bit basically instruction architecture, and then we did CC is equal to we're using Clang, and we're using the C flags as ST C11 using the standard version C level 02, I mean O2, which is the optimization level 2, G3. Oh, I don't know what G3 is, but okay, W all. So all the warnings, W extra also. Target is equal to RSV32. Nice. Freestanding, no H3 lab. Okay. And then build the kernel using $cc, $C flags, WL. Tkernel.ld, WL, map kernel.map, minus o kernel.elf, kernel.c. Start QEMU using machine word BIOS. Default no graphic serial mon stdio no reboot kernel. Okay, so that's what we were doing. So and then we ran the script. Let me just show you the kernel.c too. It'll be a revision for me also. Kernel.c. So this was kernel.c. We just were defining the memset um, function, and then we are using the memset function in the kernel main function. And then we are also defining the boot function, which calls in the kernel main function. Basically, jumps to the kernel main function after setting the stack pointer to the stack top, and yeah. So this is the assembly code for that, and then it continues on an infinite loop. So that was kernel.c. So okay, let's just run this again. So to go into the QEMU monitor, you have to do Control A and C. We're in it, and then if I do info registers, there should be the kernel.elf running, and pretty sure the PC is 8020200048. That's cool. So info registers we already did. So and there was one more command that I'm forgetting, which was to to create a specific results for our use case. Is this? Oh no, we have to do it in bash. So I'm just gonna quit this and then paste that thing here, And look at this. So boot, all of these are the addresses of the functions, mem set, kernel, main, all of these things. And you can also do this thing, check the addresses of functions using llvnm. Sorry, um, sorry. So llvm minus m kernel dot elf. So this is the addresses of the functions. Basis and ends at this, starts at this, ends at this, stack top is this, boot function and starts at this, kernel main starts at this, memset starts at this. That's cool. So you go to hello world, and apparently it says that we have written our first kernel. Okay, so I just want to know, I wanted to know before, um, I wanted to know long back, what is QEMU? Just gonna use Chat GPT for this because I think that will give me streamlined output. What is QEMU? Kilometer is an open source virtualization technique that allows you to run virtual machines on various platforms. It's primarily used for creating and managing virtualized environments for different operating systems. Okay, what makes it special is the ability to emulate multiple CPU architectures. So you're not software that is for completely different processor architecture than your host machine, or vice versa. It supports various operations from Linux to Windows to macOS, and we can work on a range of hardware. Nice. So it's just a virtualization machine, is it? So that's cool. Hmm. Nice. So we have built the first kernel. So kernel, what is a kernel? You may ask, what is a kernel exactly? If we just see what is a kernel exactly, it's just an interface between the hardware and the software, I guess. The core part of an operating system. It acts as a bridge between the software and the hardware of computer. Kernel manages system resources and ensures that different programs users can run without interfering with each other. Manage process surrounding programs. Memory management, device drivers, file system management, system security and access control types of kernel, all this stuff. Nice. So we move on to hello world. Are you able to hear me? Okay, cool. So in the previous chapter, we successfully booted our first kernel. Although we could confirm it works by reading the result, it still felt somewhat unsatisfactory. In this chapter, let's make it more obvious by outputting a string from the kernel. Say hello to SBI. In the previous chapter, we learned that SBI is an API for OS. Yeah, SBI is standard supervisor binary interface. Okay, supervisor binary interface is an API for OS kernels, but defines what the firmware OpenSBI provides to OS. Okay, okay, you should be just debugging, console, reboot issued, shutdown, time setting. Okay, nice. Okay, although we could confirm it works by reading the resident itself felt somewhat okay. So SBI is just the um, supervised binary interface, which is the API for OS. To call this SBI to use this function, we use the eCall instruction. So what did we do here is we are doing kernel.h for including that, and kernel.h is pragma once. What is pragma? Hashtag pragma. Then struct SBI ret is equal to, and we are defining a struct called SBI ret, long error, long value. When you add the SBI call function, the function is designed to call open SBI as specified in the SBI specification. So, and then we're including the kernel.h and the same thing here. Struct SBI ret SBI call. We're defining a function called SBI call, takes in 5 arguments and FID as argument and EID as argument 2. And then we're doing registered long A0 ASM. A0 is going to be assigning this. Okay. And then we're doing the another assembly code, eCall. So we're doing eCall instruction, which what does it do? It uses a control transfer instruction between the supervisor and the SEE. What is SEE? This function is called open SBI as specified in the SBI special. The specific calling convention is follows. All of us share a single binary code, um, which facilitates the mixing of SBI extension. SBI specification follows the better calling convention. eCall is used as control transfer instruction between the supervisor and the SEE. Encodes SBI extension ID. A6 encodes the SBI function for a given extension ID encoded in A7 for any SBI extension defined in or after SBI v0.2. All results except so A7 encodes SBI extension, which is this. Um, but what does this mean though? I have certainly no idea what is going on here, man. Still, a lot of things are going over my head. An e-call is used as a controls transfer instruction between the supervisor and the SEE. What is the SEE? This is kind of hard. Below calling convention. Hmm. Binary encoding was chapter 3. Um, E-call is also used when applicants call the kernel. Oh, damn it. Let's try to understand it. Let's try to understand what e-call instruction does first. Sorry. This assembly language instruction using RSV is architecture for making system calls. Okay. It stands for environment gone. Okay. An instruction where for user level programs to request services from the operating system or environment in control manner when a program must interact with the operating system, whether to access hardware, manage memory, perform some other side. It can't directly do so because it doesn't have permission to execute sensitive operation. Instead, users use eCall to make a system call which safely switches the program from user mode to supervised mode, privileged mode, where the operating system can handle the request. User mode when a program executes the eCall instruction triggers a trap execution exception that causes the process to switch from user mode where normal application code runs to supervisor mode where the application's operating system runs. Trap handling the eCall instruction invokes a trap handler defined in the operating system's kernel. The trap handler examines the arguments passed by a specific registers and processes the system call accordingly. Return to user mode again. Okay, it invokes a trap handler defined in the operating system's kernel. The trap handler examines the arguments passed via um, specific registers and processes the system call accordingly. Return to user mode. After the system call has been executed, file read or write. Memory allocation control returns to user program in user mode. The execution continues. Instruction to be called. Okay. As argument system call, the return value is typically based on suggested. Okay. The operating system needs to know which service the program is requesting. Typically, is stored in one of the registers A7RSICV to indicate the system call number. 93 in Linux. Load the exit state as 0 for normal exit. Call may the system's call. Nice. Nice. Okay, so we're doing this SPI call using the call basically, and then instruct SBI that dot error is equal to A0, dot value is equal to A1. Okay, interesting. Setting dot errors to A0 and value is equal to A1. Console put char, which is SPI call. Okay. So basically putting into the console. You're putting this to the console, and then you're doing WF5, which is void. I don't know what is hashtag pragma. Is a preprocessor directive that provides a way to issue special instruction directives that be used to control specific aspects of compiler such as optimizations, warnings, or other machine specific features. Hmm. Okay. Nice. This will disable the warning about unused variables. Mm-hmm. Nice. So what does this do? Pragma once. Okay. Okay. So you're telling me that I need to create a header file named kernel.h, and then I have to insert this, and then also insert this kernel.c. I have to modify this, and so I'll do that. So what I'm going to do is select everything in kernel.c, and then we're doing delete this, and we're doing this, save this. Okay. Let's try that. Nothing happened. Nothing happened. Okay, I think I have no time as of today, but it was good 20 minutes. Um, we'll continue from. I'll continue tomorrow morning at 6 so that we get work done. So, yeah, I'll wake up tomorrow morning at 6 and continue the stream. I'm sorry. I have to get some sleep and I have to recover from this fracture.